All right, good morning, everyone. Can you hear me well?
Yes.
Okay, so I hope you're doing well. We are going to start for the 9th tutorial today. So before we do so, let me show you one very good book I like very much, but you must already all know about it, I guess. So it's a book by Degennes, which is named Gouttes, Bulles, Perles et Ondes in French. And it's basically everything about weighting and capillarity you would need to know as a starter in the field. And it's very useful for soft matter as well, because you could, for instance, study droplets of polymer materials that are viscoelastic, so gels and so on. And the same, you can study the weighting of cells or biological objects. And so there are plenty of ideas that can come from this weighting community. Moreover, there is an increasing activity in the weighting of droplets on soft materials. And in particular, what happens near the contact line when you put a droplet on the soft materials, there will be a capillary force that pulls on the elastic materials below. And so you modify the equilibrium properties, but as well the dynamic property, the spreading laws, for instance. So there is a very active community on this topic nowadays. So, you know, it's at the boundary between soft matter and weighting communities. All right, so we will talk about something completely different today. So let me just, yes, so you have this on your screen. So we'll talk about the glass transition, very basic features. If you want to know more about this field, I would encourage you to go and discuss with Giulio Biroli, for instance, on the statistical physics aspect. But here is an historical perspective. So you have a famous paper by Adam and Gibbs in the 60s. It's really a paper that has been cited thousands of times already, if you just Google it. And it poses the basics of main ideas on the glass transition, and in particular the concept of cooperativity that we will discuss today. So you will see the tutorial is basically trying to follow the steps in this article and being able to compute the same formulas. So you can read it afterwards if you want. As you will see in this glass transition problem, there is some microscopic length scale that we call the cooperative length, which is the region in the sample where you would have a relaxation. So you have a certain size in the system that is called the cooperative size. And an idea emerged afterwards, which was the following. If there is a microscopic size in the system, perhaps by reducing the material dimensions, you might end up by reaching this size and measuring some anomalies. And this has been done with thin polymer films in the group of Dutcher by, in particular, Carrie Danoki-Verres and James Forrest, where they studied the glass transition in confined settings. And typically what they see, if you look at this paper in details, they measure the glass transition as a function of the thickness of the material. So you have a bulk value, which is here, but at some point you start to have reductions of the glass transition, very sharp change of the value with respect to the bulk one. And you seem to have lines that all cross at one very specific point. And so Degennes, who met those young researchers at that time, Degennes contributed to understand, or I mean, to try to explain this observation by introducing a concept of bridges, where you have big polymer chains that bridge two interfaces, or loops like that. And basically by saying that those bridges, they connect the heart of the material with the boundaries. And the boundaries, basically, you have a free amount of volume. So it's very easy for the molecules to move near the border of the film. So in contrast, in the center, it's pretty difficult, and you are in a glass, so it's very slow. But due to the presence of those long chains, you might have a connection of to high mobility regions. And this is basically the idea that was proposed by Degennes. And he wrote that in a very quick note in 2000, where he basically do some calculations about that and look at the probability of relaxation when you consider a path made of a polymer chain. And so we will, at the end of this tutorial, if we have time, we will try to revisit all those steps together. All right, so I've combined this into tutorial number 9. And with respect to the version that was present last week, it has been changed a bit. In particular, I added the sliding model by Degennes at the end. So this was not present last week. Okay, so let's see if we can make everything. I mean, go through all of this because it's a pretty dense program. All right. Okay, so we are going to go to the whiteboard now. Okay, I hope you can see it now. Let me see. All right, and so first of all, I'm sure you don't know much about the glass transition in general. So let me just stress the fact that it is an open problem since more than 100 years now. And according to famous physicists, such as Anderson, for instance, it might even be one of the most interesting and important problems for condensed matter physics theory today. So it's really a kind of transition, but nobody knows if it's really a phase transition like other ones. And there are as many theories as there are theoreticians in the field, so it's very difficult to solve the mystery. So let me provide a few features that are solid. So first of all, if you think about any extensive quantity, so take a material, typically a liquid, your favorite liquid, and you measure an extensive quantity. So it can be either the volume of the material, it can be the enthalpy, for instance, it can be the entropy. In fact, you don't measure the entropy, but what you measure is a heat capacity, okay? And so you can have access to some entropy variation. And let's assume that you measure that as a function of temperature. So the easiest way to think about it is to take the volume, okay? You have a material, and you know that temperature it's changing the volume by dilatation effect. You can think about any material like your door or your window that will change in size with the temperature, and in the summer it's more easy or more difficult to close it, right? So take your favorite liquid and then start to cool down the system, okay? So you cool down the system, and the material is shrinking in size, okay? In fact, you are exploring a bit less the anharmonicity of the interaction potential between the atoms, as you might know. Okay, so you are now shrinking the material, and at some point, you will reach a particular point that is called the melting point, where you have a first-order phase transition from the liquid to a solid material. So this occurs typically at melting temperature. This is the liquid, and so then you have a sharp jump because it's a first-order phase transition, and you end up in a solid material with a different slope. Okay, the atoms are completely rearranged. They are periodically put on a lattice. And so now changing the temperature will change completely the expansion behavior. Okay, so you are much more packed than in a liquid. And so the solid behavior has a different slope. All right, so this is a first order phase transition between a liquid and a crystal. Okay, something that has been very well studied and documented. However, if now you do either of the two following things. Either you go very fast, because this is a picture at equilibrium that I provided you, but you can assume that you can go very fast and place yourself out of equilibrium. You don't let the system to explore the phase space, and therefore you are out of equilibrium. Or you work with complex materials, soft materials, like polymers, and due to the fact that those polymers, they are very long spaghetti noodles that are entangled and so on, it's very difficult for those polymers to really crystallize into like the spaghetti that you have before cooking them, you know, in a very crystalline array. So it's unlikely that they will spontaneously find this array. And so you might find yourself in a metastable state that is not the ideal crystalline state. And we call that a glass, okay? So either by going fast or by using very specific material, you avoid the crystallization point, and you kind of enter a metastable state here that we call a glass or a supercooled liquid. So let me just, I will just do something else up here. We enter this metastable state and we follow the line of the liquid. But at some point, if you do so, what you will see is that your liquid suddenly changes its way of compressing or expanding, if you want. And so you enter a kind of slope that is similar to the solid one. We call that the glass. On the macroscopic aspect, your system has frozen. It's a solid object. But be careful, it's a solid object on the macroscopic vision of it. But if you look at the organization of the molecules inside, it's exactly like a liquid. They are completely disordered. It's an isotropic symmetry inside, and you don't have this periodical crystalline order like in a crystal. So it's what we call an amorphous solid or a glass. And in between the two, you have a kind of change of slope. Let me put it randomly here, that we call TG. Okay. So experimentally, you might define some crossover temperature where you see a change of behavior. Suddenly, the system solidifies, and also the way it shrinks with temperature changes suddenly. Okay, or I mean, it can be smooth. It's not necessarily very sudden. In particular, if you go much faster than what I just did, meaning you quench the system super fast, well, you might leave the metastable states before and end up into another glass number 2, and you would see another TG, which is TG number 2. So the glass transition from the experimental perspective is not necessarily well defined. It's very empirical, okay? But that's a kind of thermodynamic vision that we could propose for the glass transition. And again, I'm explaining things in a very simplified manner. There are plenty of problems in what I say, and there are plenty of refinements and very novel results. And if you're interested in that field, I would encourage you to discuss with, for instance, the statistical physics people at ENS in Paris. All right. That's for the thermodynamics. Now, let me think about the kinetics. There is another observation for a glass. You take your favorite liquid, let's say polymeric liquid, for instance, a ruler, as we discussed already, like a plastic ruler with which you do straight lines. Take the system, heat it with a lighter, and it will start to melt. So you have a very viscous liquid. So we are really in this situation where you are in a liquid state. And then, again, reduce the temperature and make it solidify. And this is a glass transition. Okay, it becomes again a plastic, and the plastic is a glass, just it's a glass made of polymers instead of silica like your window glasses. Okay, and so on the kinetic aspect, what you can do and what experimentalists do is to measure as a function of temperature the viscosity of the system. Okay, you can look at how much time you need to relax a certain stress, for instance. Okay, so this is a measurement of the viscosity. How much does it flow? How fast does it flow? So when you are in a liquid, the viscosity is pretty low, and so you have a kind of reference value at high temperature, which is the viscosity of your liquid. If now you reduce the temperature and start to feel the solidification of the material, you will see an increase of that viscosity. And what is very interesting is that, of course, at some point you cannot do more because you don't have enough time to observe things. For instance, let's assume that this viscosity here corresponds to time scales that are I don't know, the duration of a PhD thesis, for instance. Okay, you have 3 years. I didn't move during 3 years, so you can just say, okay, apparently this is a glass. The system I'm working with doesn't flow, and so you are forced to stop here, and you will call that TG. But perhaps if you have been able to wait for 2,000 years, perhaps you would have observed a modification of the system. It's so slow that you cannot just see it, but might be flowing, right? So it's a bit empirical, but let's say you fix yourself a certain time scale, and if you don't see anything in between 0 and that time scale, well, you say it's a glass, okay? And so after that, it seems that if you extrapolate that law, it seems that it diverges, but nobody really knows, at another temperature. And I will explain that in a minute. And this is completely hypothetical. We call that the Vogel temperature. But basically, you can fit the region where you have data, where you are able to see a flow, and so where you are able to measure a viscosity. Let's assume that you have experimental data points here. You are able to do that, but of course, you cannot go above because this is your maximal time scale in the experiment. And if you try to fit the crosses, the red crosses, what you see is that you have this law. So, I mean, this is provides a very good fitting of your experimental data. It's a purely empirical law. We call that the Vogel-Fulcher-Taman law. So it's VFT. We also call that the time temperature superposition, because for any temperature, immediately you have a time scale or a viscosity here. And what is very remarkable is that for all the polymer glasses, meaning 90% of the glasses we know on Earth, they would fit very well this law, which is purely empirical. And we will discuss that in a minute, but this law is a kind of Arrhenius behavior, apart from the fact that there is a divergent at finite temperature and not at zero temperature like in the Arrhenius behavior. That's the main difference. But it's purely empirical. People have shifted the divergence point, the hypothetical divergence point. Let me stress again that nobody knows what happens here in the region where you cannot measure any flow because you cannot have data points there, okay? Okay, so this is just to provide you two main experimental features. One which is kind of thermodynamical, where you measure coefficient, thermodynamic coefficient, but the only thing is that you do that on metastable state, so it's not really proper equilibrium. And you go to kinetic description, and it's another signature of the glass transition. Suddenly, the system stops to flow, okay? That's what we know. All right, so based on that, I would like now to provide you a few more details. People have started to think, and we will discuss that today, that this increasing of viscosity, this tremendous slowing down of the system on a very narrow region of temperature, is in fact associated to a crowding of the system. So you could picture a glass, and this is again a very schematic view, but a glass has an assembly of molecules that are very packed. You can think about yourself in the subway or in the tramway or in the bus you know, just at 7 p.m. when everyone is going back home, and it's completely crowded, okay? And so you are there, and I don't know, you for instance notice that there is a free seat here, and you would like to just go this way. The problem is that it's completely packed around you, and so you cannot move alone. So you need passengers around to move with you and to escape in some direction, so that there is a gate that is opening in between the neighbors, and then you can sneak in and find your seat, okay? So there is a concept that emerges that is called cooperativity, meaning that in a glass, the relaxation is not like in a standard liquid, it becomes cooperative. You need several molecules to do some coherent movement with respect to each other so that a relaxation is possible, okay? And of course, we are not living in a quantum world in this current description. So it's unlikely that all the atoms will do something coherently together, okay? So you would need to wait for a random fluctuation, a thermal fluctuation that makes the motion you want. So it's very unlikely. The more agents are involved in this cooperative process, the less probable it is, because you would need everyone to do the proper motion so that you can reach the seat. So unlike passengers with whom you can talk and discuss and say, just move, please, with atoms, you just have to wait KT. And KT is helping you to do that, okay? And so it's a very long process. And so if it's a very long process, but then you have a very high viscosity on the macroscopic scale. All right, so those are the ideas that have been proposed in the literature. And let me comment finally on the experiment I was commenting on at the beginning. If now you say, well, in fact, it means that at a certain temperature, I need a certain number of objects, Z, to move together coherently, okay? Well, therefore, it means that if you assume that you have a certain density in your material, okay, the density times a size, a certain size to the cube, if it's a cluster that is like a sphere, for instance, will be connected to the number of objects. And so therefore, as soon as you define a cooperative number of agents, immediately you have a size, psi, for this structure. It's a dynamical size, psi, that says basically what is the size of the region you would need for some cooperative motion to occur. And of course, it's very difficult to measure that size because you are dealing with assembly of atoms, so you would need to record dynamically the motion of plenty of atoms and to kind of characterize how they move. And so currently it's difficult to track in situ, in very dense material, and as a function of time, the motion of atoms, okay? So it's difficult. So there were strategies to do that. otherwise. So you could, for instance, do that with molecular dynamics. Just replace experiments by simulations. But the problem is that molecular dynamics, so far, with the current power of computers and the current algorithms, allow you to basically compute at the most 50 nanoseconds for a standard liquid, and with, I don't know, the most 10 to the 9 atoms or molecules, okay? But the glass transition is occurring on timescales that are hours, days, years. So between 50 nanoseconds and years, I mean, you need some computing power, okay? And between the 10 to the 9 atoms and the mole, I mean, reasonable bulk sizes, well, you would also need a huge amplification of the computer power, which is out of, it's not reachable today. So you have another problem. So finally, the third strategy was to say, okay, so then just create artificial glasses. Instead of having atoms, we will create colloids, okay, that are micrometric particles, and we will put some interaction between them so that it looks like an effective liquid, and we can look at the jamming of this liquid. And so there was a very abundant literature on the jamming of and the packing of oranges, but sometimes with thermal fluctuations around. We call that colloidal glasses, and it's very interesting. It's a mimicking system, although it's not a real glass, okay? But finally, there was an alternative strategy that emerges 20 years ago, which is the following. So if there is a certain size in the system, well, it means that if now, instead of having a bulk material, you start to reduce the thickness of your sample progressively, at some point you will reach that size, okay? And you might feel an effect. You might see something happen. So take a glass, very like 1 kilometer in size. It's a glass, it's a solid material, nothing moves. But then you reduce the thickness of that material, and at some point, I mean, eventually you reach one layer of atoms. So if you have one layer, yes? Is there a comment?
No, sorry, it was a mistake.
The microphone. Okay. So if there is one layer of atoms only, well, it cannot be a glass, because you see those atoms, they can just jump outside the plane, up and down. So it's very unstable to have a monoatomic film of any material. And so you see, you have a glass, but if you change the size of the system, you end up with a gas. So, or a liquid, a fluid, if you want. So by changing only the geometry of the sample, you observe a kind of glass transition. So it's a geometrically induced glass transition. And this might occur typically when the sample size is comparable to this hypothetical dynamical length scale in the system. So that is why people have started to look at confined glasses, nano glasses, and look at anomalies. And this is what we would like to try to discuss at the end of the tutorial. Okay, so let us start. The planning for today is, first, I will give you the main flavor of the glass transition in the bulk, meaning on infinite systems, as described by Adam and Gibbs, and we will discuss the main empirical features as well. And then we go to thin films of polymers and see the model proposed by Dejean and what are the good aspects of it and also the bad aspects of it. Okay. All right, so let us start. And if you have any question, as usual, you just interrupt me and orally, preferably, and we will discuss. All right. So first of all, let's think about the reference state of matter, which is the liquid. So in a liquid, the viscosity is generally given by any reference scale, let's say high temperature reference scale, and then you have some activation process. Water is behaving this way, for instance. Okay, this is called the Meyer's law for the viscosity of a liquid. And this comes intimately, microscopically, from Arrhenius behavior. You have a liquid, which is an assembly of molecules that are creating some kind of cages around themselves with other molecules. And a relaxation process is basically a process where one molecule will be able to change place or to exchange with another molecule, so that you have a relaxation of the stress or you have a modification of the structure. And so you will have a certain probability to do that, and the probability to do that motion is essentially an Arrhenius probability with an activation energy, okay, with a minus A. Okay, you have this Arrhenius process for a jump, and so now if you assume that your system is at equilibrium, you have an ergodicity property of the system, and so the time scale with respect to a microscopic reference, or not, will be simply the inverse of the probability. That's ergodicity. Time and averaging, and ensembles should be equivalent at long time scales at equilibrium. And so you end up with something which is what we wrote before. So this is for time scales, but time scales, if now you have a certain stress in the system, you can transform that into viscosity. You understand that viscosity is a macroscopic emerging feature of microscopic time scales. All right, this is for a standard liquid. Now for a glass, empirically, and this is purely empirical, everything looks like a liquid. You have another coefficient here, but the main difference is that you have a finite temperature here, which is strictly different from 0 Kelvin. And so it's an Arrhenius process, but kind of shifted in temperature. And it's purely empirical. There is no demonstration on solid grounds for that behavior. So this is, as I explained before, what we call the VFT law, which is the way experimental physicists in polymer glasses would feed their data, basically. All right. So now a bit of thermodynamics. The volume of a material is changing with temperature. And we, in general, introduce what we call the isobaric expansion coefficient that you have encountered already, which is how much the volume changes with respect to temperature when you have the pressure outside, which is fixed. So this is dilatation or expansion of any material. And if you take any material, the volume will thus typically change. So let me take a reference point where at a certain temperature, the system has a certain volume. It's just one reference point. And if I do an expansion around that point using this coefficient, basically what you will see is that the system evolves linearly with temperature. And the volume increases when I increase the temperature. This is standard expansion of material because microscopically the atoms will explore the anharmonicity of the potential, and the potential is a bit tilted, so you will explore more the potential and then have more size. Okay. All right, this is a law, and so in fact it's a Taylor expansion. You should go to a second order, third order, and so on. But the numbers are important here. This is typically for a liquid 10 minus 3 Kelvin minus 1, and for a glass 10 minus 4, typically. And here, basically the range of temperature you are scanning is pretty low. At the most is 100 degrees, where you see a notable variation, for instance, let me see, of the viscosity here. From a situation where the viscosity looks like the bulk here, and TV, you have at the most 100 degrees typically for a polymer glass, okay? So this is typically 10 to the 2 Kelvin. So you see this correction is already very small, so there is no real need to go to higher correction. So basically, that is why the volume evolves linearly in a liquid, and this is what I just represented a few slides ago, okay? And of course, if you would have a larger temperature range, you would start to see some curvature on that curve. Anyway. Okay, so now there was a concept that came in the literature that is called the free volume. We call that VF. And VF is defined as the difference between the real volume of the sample and the co-volume. This is the volume, as in the van der Waals description of gases, that is actually occupied by the molecules. If you assume they are hard spheres, well, they will have a certain volume themselves. And if you sum the volumes of every particle together, you get V0, which is the I mean, the incompressible volume. You cannot go beyond that hard sphere volume. And so what we call the free volume, F is for free here, what is the difference? Is what is the remaining volume you have once you have removed the actual volume of the hard spheres. So the free volume is basically everything that is around. And this volume is what you can use to relax. I'm in the subway, I can perhaps compress a bit myself, but it's very minor, like a few %, but then I'm really incompressible. So if I want to move somewhere, I would need people to move and rearrange so that the free volume is brought in front of me and I can go and find my seat. Okay, so the free volume is really the volume that you can use to relax as a molecule. All right, so we define the free volume this way, and there was a big assumption. First, let me just say that if there is a certain V0 scale, well, we can define a certain temperature T0 this way, so that before you remember the volume was, let me find again. Yeah, so here I decided to take T star as a certain temperature scale and V star as a certain volume scale, but I can now think about V star as V0, for instance, okay? Alors, let me see where we are in the tutorial, number 3. Yes, so here people have assumed that if you continue to reduce the temperature of the system, you will compress the molecules together, and at some point, Vf will tend to 0. So the volume of the system will tend to the incompressible volume, and you will have an assembly of oranges, and that's all, okay? No more free volume. And therefore, there should be a temperature, finite temperature, at which this is satisfied. And so now if, instead of putting a random T star and V star in the system, like a reference for temperature and volume, if now I say, well, those are the references, I can just reuse the same formula as before and write that around that minimal volume or that minimal temperature, I have an expansion. I just plug the previous formula. But now what is interesting is that V minus V naught is equal to alpha V naught T minus T0. And actually, as we just plugged it right away, it vanishes at T equal T0. So the free volume, we know how it vanishes because we know the expansion of materials. So from that, we can also write the fraction of free volume with respect to the total volume. So this is alpha V naught T minus T0 divided by V, which is here. So you have V0, 1 plus alpha T minus T0. I'm just plugging the formula before. And again, remember that this correction is pretty small here. So basically, I can neglect that. At first order in T minus T0, I end up with, I remove the V0 as well, with the expansion of free volume. So from the expansion of materials, I know how the volume expands, and it's provided by the isobaric expansion coefficient. Okay, so there is a big assumption here. Assumption was that there is a temperature, finite, at which V equals V0. So at which the free volume vanishes. And this is an assumption. We can discuss that a lot. I won't comment here anymore. All right. So now we have the free volume, and there was, in addition, an ansatz that we call the Doolittle ansatz that came in the literature, and which is basically the following. Normally, when you think about a canonical ensemble and you want to look at a relaxation process, or I mean a probability of an event, or of a configuration, I should say, the probability will be typically provided by the Boltzmann factor, where you will say, well, I have a certain energy of a certain configuration, and this should be evaluated in the proper unit, and the proper unit is the thermal energy, which is the available energy in the medium. And what Doolittle suggested is to say that, well, a glass is a kind of the same description, but volume is the most important thing. And so the fact that you're trapped, as I drew before, in a configuration where you are really jammed, like oranges and so on, what matters is the volume. If you have a lot of volume, you can relax fast. If you don't have volume, you don't relax. So what was proposed is to say that on a dynamical aspect, the probability for relaxation in a glassy system will be something like, well, replace temperature and energy by volume. Well, now the probability to relax will be difficult if I ask for a lot of volume, or it will be easy if I ask for a tiny volume, okay? And the amount of volume available is the free volume. So you see, you have the same kind of mathematical shape. There is a proposal that volume should replace energy, but it's completely uncontrolled. I mean, there is no demonstration for that. It's completely empirical, and it has been criticized a lot, by the way. But anyway, let's just go on history, and this was proposed as a guess. Actually, it's an educated guess, because if we now remember that VF is provided by this formula, we immediately have the fact that this is 1 over alpha t minus t0. And if now you say, well, let's assume I'm describing an ideal metastable liquid, so I'm in the supercooled liquid state, then I can assume that this system is ergodic as well. It's an assumption. If I do so, the time scale for relaxations is simply the inverse of the probability, and you will get 1 over alpha t minus t0. And so if you just call t0 tv, and if you just call 1 over alpha capital B, well, you end up with what we introduced at the beginning, which is the VFT law. So now you understand. Basically, it was a reverse construction, probably. People saw that there was this divergence at a finite point. They saw that volume was important, and so they constructed the Doolittle argument this way. Okay, but this is how it was proposed. And the interesting aspect that comes from that is the notion of free volume. Okay. All right. So the important thing is that now there is an identification between two concepts. This is a purely empirical temperature. I'm fitting the data of viscosity as a function of temperature, and it seems to explode. Now I extrapolate it as if it was really going to infinity, and it allows me to evaluate more or less a certain temperature for an hypothetical divergence of the viscosity. So this is one. This guy. This is empirical. And this is free volume. This is the temperature at which the free volume of the system vanishes. And so now you have an identification of the two. So perhaps the moment where the viscosity diverges is related to the vanishing of the free volume. So let us go on now and look at just the microscopic version of that. Now, if I take really monomers here, so let me consider a cage like that. Those monomers, they have a typical size A. It's also true that, so I'm saying monomers, but I mean atoms or molecules, okay? It's also true that this typical cell, unit cell, has also a size of order A, right? We are in a dense system, so all the sizes are provided by molecular sizes. And so here, we can ask the question, what is the probability for that guy to relax from its cage? And it's a free volume phenomenon. So the probability for relaxation will be, well, the volume you need, it's the needed volume, in units of the free volume. Okay? And the free volume at the macroscopic scale is something, as we said before, it's written here. It's here, the free volume is alpha, a reference volume, and T minus T naught. So it's alpha, the reference volume, apart from prefactors, it's the molecular volume, T minus T naught. So the probability for relaxation is exponential minus omega, omega being the variable here. Up. And you have here alpha a cube t minus t naught. This is the typical probability for relaxation. And now if I want to estimate that in a reasonable fashion, well, when this phenomenon will occur, meaning when will I be able to relax? Well, if the volume provided is corresponding to my size. I don't need an opening that is 10 times my size. In the subway, if I want to reach a seat, I just need the passengers to move so that they create basically 50 centimeters so that I can just sneak in, right? I don't need a kilometer to pass. So the typical probability will be when omega or W is equal to a cube. Okay, so this is a typical probability scale, which is, and this is our reference for a relaxation in a glassy material at the microscopic scale. Okay. And so in an ergodic description, this can be connected to a ratio of time scales. This is molecular time scale. This is relaxation time scale. And this will be the inverse of the probability. So, sorry, there was a minus here. And so a plus here. Up. So the time scale increases when I'm getting closer to this vanishing of the free volume. And just for our numbers, T naught is an atomic scale or molecular scale, so it's a few picoseconds, typically 10 picoseconds. So it's 10 minus 11 seconds. And the temperature at which you start to leave the liquid behavior. So let me go back here. So let's call that the critical, not the critical, the cooperative onset, the moment where you cannot relax anymore as a liquid, but you start to need others to move together. So let's say 5 p.m. in the subway, where you start to have people going outside work and you start to pack a bit more the subway. Then you will leave the standard behavior of liquids to reach the supercooled liquid branch. And so this typically occurs, this is coming from experiments, but basically this is 100 degrees above really the divergence point, the effective divergence point. So if you put numbers, you have here exponent. So let me take another blackboard. So you have tau, which is tau naught, exponential 1 over alpha t minus t naught. And when t is equal to tc, the cooperative onset, then tau c is equal to alpha tc minus t0. And so if I put orders of magnitude, this is 10 minus 11, we just say, then I have exponential of 1 over alpha. Alpha for a liquid is 10 minus 3. And then tc minus t0 is 10 to the 2. So you end up with something like 10 minus 11 exponential to the 10. And exponential is something like 3. So 3 to the power 2 is 10. So you have 10 minus 11, 10 to the power 3, something like that, or 10 to the power 5. Okay, 10 to the power 5, which is what? Which is 10 microseconds. Okay, so this is an interesting feature you want to remember. Molecular timescales are picoseconds. It's related really to the motion of the cloud. It's related to the motion of the molecules when it's alone and not crowded. But then when you are in a liquid environment, well, you have some constraints. The molecules are very densely packed. And so you need some time to jump outside the potential barriers created by the neighbors. And so the liquid timescales are much higher, larger. And so it's more the microsecond. And the glasses, as we will see soon, meaning when T reaches TV and not TC, then it can explode and become days, years, and even infinite, because in this description, the time scale is diverging. All right. So you have time scales, atoms, picosecond, liquid, microsecond, and then you start to increase a lot the time scales because you are going to the glass, and the glass can be hours, days, years, and so on. There is a famous experiment, by the way. It's called I don't know if you saw that. It's in French. It's bitume. It's a droplet of a very glassy material that is every I don't know several years released from a tube. So you have a tube with a liquid inside, but the liquid is really stuck. And on a very, very, very slow time scale, it detaches, but you need to wait years and years before it happens. And I think recently, one droplet was released. Okay, so it's a very famous experiment where you have actually a super viscous liquid that on normal time scales is a solid. It's a glass, it's a bitume, but on longer time scales, actually it flows. Okay, it relaxes. All right, so this is done for part number 1. So now we are going to, no, sorry, it's not done. So now we are at question number 6. All right. So as I told you, the glass transition is something completely empirical. Okay, so we can associate it to a certain time scale. So let me define it. In general, I can say that the time scale in molecular units is given by the Vogel-Fulcher-Taman law. So it's 1 over alpha T minus T0. It's the free volume law, if you want. And then if now I'm defining TG, I need a typical time scale. And this is the experimentalist who decides. I can wait a PhD thesis. And if it doesn't move during a PhD thesis, it's a glass. Okay, I can wait an hour. I can wait 10 years, whatever. But I have a time scale, tau G. And so as soon as I have a time scale, well, the temperature is fixed, and this is what we call TG, kinetically speaking. Very, very empirical description. Of course, the fact that there is a log here hidden, I mean, the inverse of the exponential is a log. Sorry, there is a question here.
The question, it's just the link to the live stream of the drop.
Excellent, thank you so much. So what is the translation of bitume? What was the material? You know?
I think it's called the pitch drop experiment.
Oh yeah, that's it. That's the pitch drop experiment. And but I don't know what is the okay. It's a kind of bitume, right? Very viscous, oily system. Okay. Anyway, thanks very much for the link. So there is an exponential behavior. So if I just go to the log, the inverse function here, I have something which is writable this way. And you can see that, you know, this is 10 minus 11. And whatever I put here, I can put a second or a year. Let's say I can put a second is 1, a year is 10 to the 7 seconds, okay? But you see, what it will change is that this log will go from a value of, I can put 0.1 if you want to. It can go, the log can go, I can call the log, by the way, L. L can go between whatever. It's when it's 0.1 and I have 10 minus 11, it's 10. And when it's 10 to the 7, I have 18, okay? Let me just put tentatively a window for L. But you see, either I take a second or I take a year, it doesn't change much, at least only a factor 2 on this logarithmic scale. So the fact that there is a log, that is why we don't really care experimentally if we say a glass time scale is a PhD or it's a month or it's a second. It doesn't change. It's a long time scale and there is a logarithmic saturation occurring. So basically I would say, but let me just take a random value, 20. Okay, that's order 10. Between 10 and 20, okay? And so what I can draw from the previous picture is that TG, then in this plot, is T0 plus 1 over alpha L, by simply inverting the previous formula. So as soon as you have defined L, which is equivalent to defining the time scale tau G, then you immediately have a temperature associated with from the free volume picture. And if we put orders of magnitude, Tg minus T0 is equal to 1 over alpha is 10 minus 3, and L we said it's 20. So it's typically, if I put a 5 here, it's 5, it's 50. So Tg minus T0 is 50K, which is very reasonable. Remember here, I have Tg, I have Tc, which is, I told you, typically, those are not a strictly equal sign. It's Tg plus 100 Kelvin. And so Tg is somewhere in the middle. So this is 100. And this fact, this is 50. So sorry, the drawing is not to scale. Basically, you would have an hypothetical divergence. 50 degrees above that, you have the moment where you cannot see anything, which is typically Tg. And 50 degrees above that, then you reach a standard liquid. Okay, so everything is going on in a very narrow temperature region. And the free volume picture allows to get the good orders of magnitude, despite it has plenty of problems otherwise. We will discuss that later. Okay, actually we will discuss that now. I just see the tutorial, question number 7. So question number 7 is, what are the limitations of such a description? So first of all, there is a major one, which is interesting, is that it exists, there exists what we call isochoric glass transition. So you have systems where the pressure is not maintained, but the volume is maintained. And so, of course, there you won't see any vanishing of any free volume, right? The volume is constant. So all the argument about the free volume and so on is completely bullshit for those systems. Okay. But then people are arguing that, well, but in that case, replace the volume by the pressure, of course, the coupled quantity, and redo the argument with pressure, and then you would have a proper glass transition. Okay. Anyway, it has been criticized. Second aspect, the existence of a certain finite temperature at which the free volume equals 0 is also kind of very criticizable, because we are not dealing with oranges, art spheres. We are dealing with atoms. And atoms, there is no incompressible size. Even the nucleus, you could continue providing some thermal energy and continue gramping, climbing your potential, and so with thermal energy you could go to really to 0 temperature and continue to increase the travel on energy barriers. So there is no incompressible limit. You don't have an infinite barrier suddenly. You always have slopes, and KT allows you to go on those slopes. So basically, this says that if you look at the potential and interparticle distance, typically, well, you could go to really an interparticle particular distance, which is 0, provided you provide a good amount of thermal energy. And so saying that there is a finite point somewhere where you cannot go on is very abrupt as a description. StatPhys doesn't say that. Molecules that can still compress even more and even more if you just provide a good amount of energy. So this says that, in fact, it might be an Arrhenius behavior simply. So you see, criticism. Another criticism from this picture is that people have studied glasses near the glass transition with plenty of techniques. And in particular, they have revealed the existence of what we call spatial heterogeneities. Geneities, yes. Which are the following. You have some places in a glass where the system is very dense, where there is no relaxation, and you have other places where actually it's pretty soft and it relaxes well. And then you have a system which is a collection of different clusters where the dynamical properties are different. However, the description in terms of density and volume is kind of homogeneous, right? You don't have major modification of the density in a condensed matter system, in a condensed phase. And so it's unlikely that you have big kinetic differences when you have very less structural differences. And so it's very difficult to connect the free volume picture to those real observations of heterogeneities. And finally, and perhaps above all, despite this free volume description and the dynamical and kinetic descriptions of the glass transition are interesting to most experimental physicists, okay? This is a fact. People doing experiments with glasses, they are really measuring at the moment where nothing flows anymore. It's really important to them. Some physicists think that there is behind this, I mean, boring slowing down of materials, there is a real phase transition somewhere, hidden, okay? And existence of a critical point with a real change of phase in the system. And of course, the free volume picture, which is purely dynamic, kinetic, which is dealing with metastable states of matter, cannot address those equilibrium transition points. And so there are plenty of researchers, including at INS in Paris, for instance, who are really trying to reveal the existence of this underlying phase transition. And the problem with free volume is that, I mean, this doesn't help at all. So you see, you have plenty of criticism, and you should be aware of that when you deal with free volume picture and cooperativity. Any question on that? No? All right, so let us move now to cooperativity, which is basically the second important historical concept after free volume.
I have one question.
Please.
Are there models that give the same dependence in temperature without talking about free volume, or without saying that the free volume is a volume where there is a T0 where VF equals 0? Yes,
there are plenty of models. There are more models than there are theoreticians or physicists in the field. Nobody knows the answer, but there are plenty of models. So to answer your question, yes.
Okay.
You can think about, when you have the fact that there is a slowing down and this VFT law, you can think about plenty of statistical physics models to obtain that. The question is, what is the good one? And does it contain all the ingredients I've discussed so far? And today it's an open problem. There is no Nobel Prize for finding the glass transition problem. There is one Nobel Prize for the superconductivity demonstration, okay? So it's really one of the big open questions in theoretical physics in condensed matter, okay? But you're right. There are. I mean, I'm talking about you know, almost 70 years ago now. The first theoretical attempts to describe the glass transition. Today there are plenty of ongoing work and progresses on that problem. So if you're interested in that, discuss with the Laboratoire de Physique Statistique at INS. Okay, they will tell you the more modern picture. All right, cooperativity. So historically, is the second big concept that was proposed, and that has some very good aspects to describe the relaxation of a glass. So let me take a material. It's a glass, and to simplify the discussion, I will take a mole. So I have really 10 to the 23 atoms, and let's assume I can divide the material into sub-packets. Where inside each packet you have a collection of atoms, but the criterion is that this size is sufficient for the relaxation to be only inside a sub-packet, a cluster. So in a sense, clusters or blobs, if you remember the discussion about polymers, becomes independent objects. So if I'm able to subdivide the system into typical clusters into which the relaxation goes on, but where you don't need two clusters to interact for relaxation to occur. In each cluster, you have typically Z particles. Well, you will subdivide the system into n times the number of clusters times the number of objects in one cluster. So this is your system. And each cluster will be characterized thermodynamically by a certain energy and a certain volume, okay? So here the idea is to study the individual partition function for one cluster, and to say that we are working at constant temperature and constant pressure because we are like chemists working in the lab, and those are the imposed quantity by the reservoir. So the good ensemble is the PT ensemble, not the canonical ensemble. Okay. So we are in a PT ensemble, meaning that the good potential is the Gibbs enthalpy or the free enthalpy. The free enthalpy. Okay, if you go back to your StatPhys courses. All right. So let us write the partition function for one cluster. So in the PT ensemble, the partition function will be the sum over all energies and all volumes, a density of state, density of energy and volume, it's a number. How many states do I have with this energy and this volume? And then the factors. So the factors are, sorry, let me just erase that because it's useless for me here. I mean, it's annoying. So exponential minus beta E. This is the Boltzmann factor like in the canonical ensemble, but then I am in the PT ensemble, so I have a PV correction to that. Pressure is imposed as well, not only temperature. Okay. So this is the partition function, and as you know, G, the potential, the free enthalpy here, is just defined by the logarithm of the partition function, which is equivalent in saying that Z is equal to exponential minus beta G. Okay. And remember your thermodynamic courses, G is strictly equal to mu, the chemical potential, times the number of objects. Okay. And so the chemical potential appears here. All right. So this is the partition function for any cluster. And now we don't discuss what size this cluster should have in practice. It's just very mathematical, if you wish. All right. So now the idea is to deal with relaxation, motion, kinetics. And so if we take this cluster here, not all the configurations will allow you to relax. So for instance, let's assume that the volume is very small. You know, this cluster can have plenty of energies and plenty of volumes. I mean, this is the variable that is put in the sum here. And so this basically is going from 0 to infinity for each. So if now I assume I have a vanishing volume for that cluster, it's very dense inside. So it's very unlikely that you will have a relaxation. Okay. Same from the point of view of energy. So what you could say, and this is what has been proposed by Adam and Gibbs, and I mean, you can criticize it or not. You can say that only a subpart of the sum here, of the sum over EV, will contribute to relaxation. Okay, only some states will be sufficiently diluted or will be able to allow for a relaxation. So what you can say is you can define Z prime, which is a restricted partition function, which is a sum over the energies and volumes for which relaxation is possible, and it's only a restriction of the previous one. And then I just copy paste the previous expression. Okay, so you define a reduced partition function, and so it's equivalent to defining a reduced enthalpy, and thus a reduced chemical potential. And I can always say that this chemical potential is the previous one plus a correction without any loss of information here, or generality. Therefore, we end up with the following picture. All right. And this is the actual partition function of the problem at equilibrium. Okay, so Z prime is the proper partition function, but a correction that has the following form. So what about the sign of Z prime minus Z? Look at that. In Z here, you have a sum. This is a density, it's a positive number, and you have exponentials. Those are positive numbers. If now I restrict this sum to only some values of energy and volume, well, the resulting object is smaller. It's positive, but smaller. So it's pretty clear that Z prime should be smaller. We don't know how much, but it's smaller than Z, which places a constraint on delta mu. Delta mu is necessarily positive. This, strictly speaking, I could put the equality inside as well. All right. So then, what is the next question? So we are dealing with the probability of relaxation. So it was question number 2. Yes. So now I have a partition function for the total characterization of the system, and I also have a reduced partition function that only counts the configurations, the microstates where you have relaxation. So what is the probability, according to you, for relaxation? Well, it's Z prime over Z. Okay. This tells me among all the states included in Z, there are some that contributes to relaxation. And so the probability for relaxation is just the weighted partition function like that. And so I end up with exponential minus beta Z delta mu. So this is the probability for a certain cluster of size Z to relax, okay, with a delta mu which is positive. So it's indeed a number that is smaller than 1. All right. Okay, so then we want to study the relaxation of the system. So now we have to be a bit more precise in what we say here. I told you that I have several objects that are relaxing. And so we need to define what a relaxation is, okay? So a relaxation is a situation where 2 of the objects, for instance, the yellow one and one of the red ones here, will change place in the cluster. And again, the cluster is defined so that it's completely independent from the other clusters. So everything should happen inside the cluster. So if you have the inversion of 2 objects inside, it means that there is at least 2 configurations for that cluster. So the entropy has a minimum bound, which is KB log 2. Okay? So let me introduce that. If I introduce the configurational entropy, configuration, so I'm not counting any motion due to temperature here, but only the configurations is the subpart of the entropy which is related to configurations. Well, SC, it's KB log of the number of configurations, and relaxation is possible only if you have at least 2 configurations. Otherwise, you cannot relax. If you have 1 configuration, it's stuck. So you need to have at least 2 configurations, which places a lower bound for SC. Good. So now we have to remember that the system is an assembly of independent clusters. So the total configurational entropy of the system is an extensive quantity, by the way. The total configurational entropy for the ensemble, I mean the molar entropy, because we are dealing with 1 mole of atoms. The molar entropy of configuration is simply the number of clusters times the entropy of configuration per cluster. Okay, and so I can now replace, remember, n is connected to the total number of objects divided by the number of objects inside one cluster. And so this should be bigger, as we just say, than Avogadro number Z, and SC is bigger than KB log 2. All right, so I have a relation between the macroscopic configurational entropy of the system and the number of objects in one cluster. So I can reverse that relation, and I end up with Z that must be bigger than a certain Z star that I call NAKB log 2 over the entropy. So if the system has a certain state, it has a certain entropy. And in this entropy, there is a configurational part, which is related to where the atoms are, and not their motion, but the positions, if you want. This configurational entropy is given. I have some constants. The Avogadro number is the number of objects in the system. KB is known, and 2 is a number. So it means that for relaxation to occur, the cluster should be minimally set to have Z star objects. I cannot create clusters smaller than that because they won't relax. So they are not clusters by definition. The definition of a cluster is the minimum. I mean, it's an object that can relax alone without the need for neighbors. Okay, so I have a lower bound for Z. That is interesting. We will see why in a minute. Any question on that? No? All right, so this is the next question now. What we did so far is to estimate P, the probability for relaxation to occur within one cluster. So in fact, I should stress the fact that it is depending on how I parameterized the system and how big were the clusters. I mean, I have just drawn some clusters and fixed Z, but this can be anything in particular. So the total probability for relaxation, P tot, if you want, will be the sum over all the possible values of Z of the previous PZ. I'm doing a partition, and I assume that they are all contributing equally. And so, why this is important? Well, it is important because it places a lower bound for this summation. So this is not a sum from Z equals 0 to infinity. It's a sum from Z equal Z star to infinity. And that's really the crucial aspect. You will see why in a minute, because this becomes really a very simple geometric series where Pz is exponential minus beta delta mu to the power Z. And so it's very easy to compute. You have the first term, and that's the key step. Now I have a bound which is non-zero, so it's dominated by the first term, this exponential series. And then I have a correction that is 1 minus the raison here. I don't know how to say raison in English, but I mean, you know, this guy. And remember that we are dealing with a glass. I mean, we are describing a super cool liquid, but something that is pretty slow, more and more like a glass, and it's slowing down, and so on. So if it's slowing down, it seems that those probabilities, they are in fact much smaller than 1. You have a very weak probability of relaxing because it's so packed and jammed and so rare that there is a relaxation that on the macroscopic scale, you don't see anything flowing. So this number should be very small, which means that typically the kinetic, I mean, the barriers that we are putting here, the chemical potential barriers, they must be much smaller, much larger than KT. So, yes.
Delta mu does not change because it does not depend on Z, it only depends on the size of the system and the temperature and the volume, but not on the number of...
Yes, and it could depend on the temperature. In fact, it could grow as you reduce the temperature. Yeah. But we assume here that in this description, we will assume that it's a constant. Okay. But you're right. It can depend, and in fact, it could perhaps depend on the fact that you have different numbers of objects. So when we wrote that here, when we wrote that line, we assume, as you said, that delta mu is a constant. But you could refine that picture, and you could then do some numerical computation of the series. Thanks. Okay, so coming back to my point, we are dealing with asymptotically with the moment where it becomes a glass and super slow system. So really asymptotically, I don't care about this denominator. The barriers are much higher than KT, so your system is trapped at the bottom of a potential, and it's unlikely that it will jump to another state. It's really trapped. It's a glass, okay? So basically, this is 0. And so you are left with the fact that the typical probability for relaxation is interesting, is something like minus delta mu over kBt, but Z star. Only Z star matters. In this series, we really don't care about the larger values. They are exponentially smaller in size, so they don't contribute, as usual with geometric series. So we are dominated by Z star, the minimum value for the size of a cluster. And so this is what we call the cooperativity. Z star is identified as what we call the cooperativity. The minimum number of objects needed to relax is the typical number of objects needed to relax. Because if you add some of them, it will exponentially be less probable. Okay. And so now I can replace it by its value. And I don't remember it, but I will come back a few slides ago. Yeah, it's here. So it's Avogadro number, KB, log 2 over SC. And so I can simplify it. And then I have SC times T. And a priori, SC can be a function of temperature. So it's something like a constant T and the configuration entropy as a function of temperature. So it's interesting. Now we are relating the probability of relaxation to a thermodynamic quantity, which is the entropy, the configurational entropy, which is related to the number of conformation macroscopically the system has. And it can be a function of temperature, and we will estimate it based on thermodynamic arguments. So that is an important result. That's how the configurational entropy became a very central quantity in glasses. If you have an assembly of objects, pretty dense, can you estimate the number of allowed configuration? And this will be related to the ability to relax or not. It's also interesting because it makes a very big connection between glasses, systems where you are stuck in terms of relaxation, and information theory. If you want to compute a certain problem, this problem might be a certain number of equations to solve. But at the same time, you have those coupled equations, but you might have some constraints. And if the number of constraints start to grow, at some point there is no more solution in the problem. If you put too many constraints, well, you won't find solution, okay? And so it's like a glass. This is the computer will not be able to find a solution because you are increasing the number of constraints. And so it will take ages, if you want, to find a solution. So there is a parallel between algorithms for computation of difficult problem and glasses, which is a material problem. And at ENS, for instance, there is a group of Florent Zakala and Lenka Zdeberova who are working on that. It's very interesting. They are really mapping glass transition problems to information theory and computing problems. So if you're interested in that type of physics, I would encourage you to discuss with them. All right. So that is the end for this parenthesis. Let us now go back to thermodynamics, and let us define more precisely what we say when we talk about configurational entropy. So let's again take our favorite cooling diagram, where we take now as an extensive quantity the entropy of the system, the molar entropy, because we are dealing with 1 mole from the beginning, but let's say the entropy as a function of temperature. Again, the entropy is reducing because you are stabilizing the system. There is less and less configuration. So really, you are reducing the entropy of the system when you are in the liquid branch. At some point, there is a first order phase transition, and you end up in a crystal, and the crystal is a solid with a different slope, exactly like for the volume. Okay, and you could also stay in a super cool liquid state, and then reach a glass or the crystal or whatever. And so what is interesting is that what we call the configurational entropy is the entropy related to the position of the atoms, but not their KT motion, because you also have entropy due to the fact that there is an oscillation in your cage, if you want. And so by subtracting the entropy of the liquid and the entropy of the solid, you define what is the configurational entropy. This is what is left behind when you remove all the kinetic aspects. So let's say the typical center of mass positions. How many configurations do you have for those typical center of mass if you neglect the oscillation within one position? Okay, so that's a definition, in fact. And so what is good is that we didn't know so much about the SC, but we know very well the entropy. In particular, we know the heat capacity, and the heat capacity, let's say at constant pressure, because we are at constant pressure, we could do at constant volume if we wanted so, is simply given by a partial derivative of the entropy with respect to temperature at constant volume. Okay, I should specify what is constant. The number of objects is also fixed to a mole and so on. Okay, so this is CP. So it's interesting, then I can say that SC is equal to delta CP, which is CP of the liquid minus, sorry, what did I say here? It's wrong. Sorry for that. That is correct now. If I derive the configurational entropy with respect to the temperature at constant pressure, multiplied by T, this is the difference of the heat capacity between the liquid state and the solid state. We call that delta CP, and it's another very important quantity in glasses, and this is something you can measure by measuring how much energy is accumulated inside. I mean, this is the heat capacity, okay? The variation of energy with temperature. Okay, and so then we do an assumption. Delta CP should be a priori a function of temperature, but we will assume that in the narrow region where we are looking at things, 50 degrees around the glass transition, we assume that it doesn't depend on temperature, to simplify the discussion. This is actually observed experimentally, but if you would have a slow variation of temperature, you would just do the next computation numerically. I will do it analytically now, but you can correct. This is not a major point. So I told you that T dsc dt at constant pressure is equal to delta Cp. And it is a function that doesn't depend on temperature. So I can simply write, and I forget the fact that the pressure is constant. Now you know that. I don't write it down anymore. I have that. And so it's easy for me to integrate that with respect to temperature, keeping the pressure constant. So SC will be some reference value plus an integral between some temperature reference okay, and thus, due to my assumption, This is delta Cp times the log of T over T star. Again, you can refine this if you know a more precise expression of delta Cp with small variation with temperature. It will be evaluated numerically, and that's it. But the main feature is this one. There is no major point here. The major point will come now, in fact. The major assumption. So for now, what I wrote here, C star is simply a constant of integration. So T star and C star and SC star, sorry, they are, I mean, I have freedom to decide to fix them. But then there was a proposal by Kaufman. It's a postulate. We say that, let me go back to this picture. We say that, and it's an assumption, that the entropy, the excess configurational entropy, so the green arrow, would go to 0 at a finite temperature. Might be true, might not be true. You could really reach the solid state on my drawing at 0 Kelvin. It's not clear that you will cross the line, okay? But based on what I said previously, if you prolongate this line, the supercooled liquid state, it seems that there is a crossing point at a certain temperature that we call the Kaufman temperature, at which and below which the entropy of configuration will become smaller than the one, I mean, smaller than 0. So it will mean that the entropy of the liquid will become smaller than the entropy of the solid. This is not possible. The solid is the most ordered state in condensed matter, right? I mean, it's an open problem, so I might be wrong in what I just said, so be careful. But according to our intuition, this is not possible. The entropy of a liquid should be always larger than the entropy of the solid. Therefore, if there is a point at which the entropy becomes, the configuration entropy becomes smaller than 0, so the entropy of the liquid becomes smaller than the entropy of the solid, therefore, there should be something happening here, a phase transition. We should change completely the physics. So Kaufman, based on those drawings, said there should be a finite temperature at which there is a real phase transition going on. Nothing about dynamics. I mean, a fundamental change of properties of the system at equilibrium. And this is what the people working on the statistical physics aspect of the glass transition are dealing with. I told you about the existence of a potential critical point or a potential real universal point at which a phase transition occurs. Well, they are looking after that exactly. Okay? Does it exist? Is there a new kind of phase transition or a hidden phase transition in a glass? So this is a very interesting proposal, but just look at what it means practically now. Practically, it means that there exists a temperature that is finite at which the critical, sorry, the configurational entropy reaches 0. That's the definition of Kaufman. Therefore, let me don't take those reference values randomly, but just choose Kaufman temperature. I fix T star to be equal to Tk, and I fix the configurational entropy SC star to be the configurational entropy at temperature Tk, and thus, from the postulate, to be 0. Therefore, the previous formula is modified. Sc becomes strictly equal to delta Cp times the log of T over this magical temperature. And I can do an expansion near the critical point, near Tk. So this is delta Cp log of 1 plus T minus Tk over Tk. This is exact. But now if I Taylor expand it, I will just keep the first term. Okay, you see where I'm going now. Now, it seems that the configurational entropy is vanishing linearly with temperature, near the critical point. Remember, here, we were saying that the typical probability for the system to relax goes like 1 over temperature, but this is not changing much, over configurational entropy. So there should be a vanishing of the probability and an explosion of the relaxation times that looks like the VFT law. So if now I plug that into the system previously, P dot exponential minus C over T, this is equal will become dominated by, let's say, the TK value, TK, and then delta CP, T minus TK over TK, so I will remove that. And I neglect the second order correction. We should be careful, we are dealing with equivalent within exponential, okay? But let me just put a scaling symbol here, okay? The dominant behavior. Good, so P dot is like that. So in a sense, if I write B is equal to C over delta CP, and if I write TK to be TV, and thus remember we also identified to T naught, all the temperatures that we've discussed so far, well, it seems that this is the VFT law again. It's the VFT law again, and so the time for relaxation is the inverse of that probability in an ergodic description, and so you recover the empirical behavior. So you see, we have a temperature that describes the empirical fitting of the viscosity. We have a temperature that describes the phenomenology of free volume, at which point the free volume vanishes, and we have a third temperature proposed by Kosman at which the configurational entropy vanishes, which is related to free volume. But those might all be equal, and so there should be a real phase transition that is occurring at, that is occurring at a point TV, but that you cannot see because while reducing the temperature, at some point you reach TG, which is a boring object, purely kinetic, and the system becomes so slow that you're not able to find the equilibrium, you're not able to find this TV point because you cannot measure any relaxation. It's too long for humans. Basically, it's as if you were looking at a liquid where there is a phase transition, but you're an object that is living in a very short time scale. You're like a molecule. And so you cannot look at long time scales for equilibrium to be reached, for any phase transition to be fulfilled. And so perhaps as human beings, where we are dealing with glasses, we would be too short-lived in terms of time scales to be able to see the existence of a real phase transition that is there, but it's completely hidden by out of equilibrium aspect, metastable objects. Okay? That is the enigma of the glass transition. It's an open problem. It's been 100 years that people are trying to find the answer of that, and it's an open question. But you see now why it's an open question, what are the interests of it, and what are the aspects of it. If you want to know more, go and see specialists. What I would like to do now is to come back to soft matter and polymers and tell you a bit more about this very smart idea that has been proposed in the literature 20 years ago. If there is a certain size for cooperativity here, it means that by looking at nano glasses instead of bulk glasses, you might measure that size. And that is a completely different world. If you want, it's the glass transition, but in confinement. And the claim is that if you are able to understand it, you will learn about some bulk quantity, which is Xi, and therefore you might come back to the main problem. Okay, that was the motivation. Any question on those aspects? No? Okay, so now we go back to polymers. And I hope we have time. Yes, we have a bit of time. Okay. So this is the sliding model by Dejean. So the system is the following. Now I'm dealing first as a reference with a bulk material. And in this bulk material, I have an assembly of chains. So it's really the plastic ruler that you have to draw lines on your paper. It's a plastic material. Inside you have very long spaghetti noodles like molecules, polymers, that are all entangled together, but they're frozen. It's sufficiently low in temperature that it's very difficult for them to move and to relax. So it looks like a solid. It's a glass, okay? We call that a plastic for historical reasons, but it's a glass. It's another kind of glass. Those polymer chains, they are made of monomers. You know that very well now. Sorry for the quality of the drawing. A large assembly of objects. And so Dejean said, well, when we have a glass which is not made of single molecules like your silica window glass or car glass, but it's a plastic, it's an organic glass made of long polymer chains. Well, it's true that every monomer behaves like in a standard glass, so it can relax and do some free volume motion. For instance, this guy can really oscillate within its own cage and exchange position with neighbors in a free volume fashion. So we are back to the main glass transition problem. But due to the fact that there is a topological constraint that has been added at the microscopic level, now there is the possibility to relax in another fashion. Let's assume that this guy, the teacher, for instance, if you think about a class with very young kids and the teacher was doing the end to the kids behind, when this guy is moving in the subway, this person is the only person that has to talk to people and push people around to move. But behind, the young pupils, the young kids, they just follow. Okay, they don't have to play the free volume game. They don't have to talk. They don't have to push or to fight to move. Okay, so what does it mean? It means that the guys after that simply have to follow. So there is an aspiration like, so you can just follow the leader, and there is some room for you in a tunnel that you can just sneak in, and there is no price to do that motion. Okay, so Dejean said then this mechanism can be interesting because there might be an easy way of relaxing in a polymer glass. Okay, so let's try to estimate things more precisely. So let me give one definition. When the orange guy is moving, it doesn't need a big free volume. It needs typically, so let me call it I, is number I. When this I is moving, it needs a certain free volume, omega I, which is in fact much smaller than its size. So if you think about the free volume picture before, I was telling that to relax, I will have to pay a probability which is the exponential of a certain, with a minus sign, of a certain volume needed in terms of free volume available. But the volume needed is very weak for the particles along the backbone. So you have omega I, which is much smaller than AQ. And so the probability to relax, it will be a free volume-like probability. So in terms of free volume, and the free volume, we already discussed that for a monomer is A cube alpha T minus T naught. This is the microscopic version of the VFT law, and we already discussed that. But the key parameter in the Dejean's proposal is that you don't need A cube anymore. You need a much smaller volume because the leader has already done most of the work. Okay, and so Dejean made another comment. He said, first there is this, but there is also the fact that not all the monomers are equivalent. One might be more crowded than the others at some places, or one might be less crowded than the other. So in fact, Dejean says there's in fact a distribution. Sorry, so this was proba of relax. Proba of relaxation with volume omega I. But there is now a distribution, I should change the name. there is a distribution for omega I. So there is a capital P of omega I, which is, well, I will shoot for any monomers in the backbone for what is the typical volume it needs to relax. And so this, according to the gen, is is a Gaussian tail distributed. So it's a Gaussian-like shape, the tail, where, as I told you, we want to have that satisfied. So where the typical variance, or here the standard deviation, sorry, should be much smaller than a cube. So it just adds some distribution for omega I. But then the idea is to calculate the average relaxation time. So the relaxation time is the product from I equals 2, if I start here and this guy is 1, to n, the final one. The probability, the time scale is the inverse of the probability, so plus omega I over Vf. This multiplied by the probability of the first guy to move, so P1 if you want. And I can call that N1, P end, probability of the end to move to the power -1. It's a constant. Is there a question apparently? Why centered on 0? Well, this is a big assumption. My feeling, and I don't control this statement, but it's a feeling. My feeling is that the gen proposed this distribution in a reverse engineering fashion so that it allows to explain the data at the end. That's a feeling that's completely uncontrolled, so be careful. It comes, you can read the paper, I sent you the papers. You can read the sentence, it just says, assuming that the free volume of each monomer to be Gaussian tail distributed and not Gaussian.
Yes, but I can see why it could be Gaussian, but why would it be centered on 0?
That's what I just said. I said
that's
no,
volume.
Yeah, I agree with you. I said the gen said it's Gaussian tailed distributed, meaning that it's the tail of a Gaussian. It's not Gaussian distributed, so it's the same. You're talking about the average. I'm talking about tail is the same statement. I would have expected this to be centered on the average omega naught. Instead of having a Gaussian distribution, he says explicitly in his paper in one line, we assume a Gaussian tail distribution. So not centered on omega naught, but centered on 0.
Okay, so we don't know what is. We don't know the probability for small omega.
Either that, or there is an assumption that we don't really control in all this, which is why you asked the question. So I'm just giving you the arguments by the gen. I don't really understand that step personally. Others from being the one that allows you to get the good result at the end. And someone has to now show that it is a genius intuition, okay? But I'm not able to do that. Perhaps people who are familiar with stat-phys problems might see that, oh, of course, it's Gaussian tail distributed. This type of problem, we already saw that it was always Gaussian tail distributed, so it's a good intuition to, but I don't have this background. I'm not sure I understand that step, okay? Read the paper by the gen and make your own opinion. As you will see, this is the key step that allows you to get the good result at the end. If you don't do that, if you put a Gaussian as you wanted to do, it doesn't work. I tried it. So either it's magical or it's an educated guess. I don't know. Anyway, that's what I wrote is the time scale for some process. But now I need to average this using the probability. So what we are interested in is what is the average time scale. So I should average all that against the capital P distribution. And so this will be written. So let me, here there is of course a norm in front and to normalize the probability. We don't care, you can calculate it. It's Gaussian tailed, so it's easy to compute. Okay, so tau over tau naught. Let me check the time. So yes, we have still a bit of time. We should accelerate though. Should be the end term, which is a constant. And then you have n times or n minus 1 times the same integral here. So let me call it with the integral being for 1. We are here, of course, assuming with this product that the monomeric motions are independent. We made a strong statement here. Okay. So I should integrate over omega I between 0 and infinity of the distribution that is the Gaussian tail distribution with a certain norm. And what I want to average is this guy. So this doesn't depend on I, so I can it doesn't work. Okay, anyway. And up. Sorry for that. So I'm left with a quantity that doesn't depend on I. That is why there is n minus 1 power is here. So let's just group everything. As usual, we can complete the square. So you have minus omega w square root of 2 omega w0. Then you have a minus 1 over vf multiplied by omega naught, and then the square root of 2 squared, so that you end up with omega over vf if you multiply those two terms. Minus minus gives a plus, yes. Then there is a squared, so you need to complete by this guy 2 times. Okay, and so this is n exponential omega naught squared 2 vf squared. And then I should transform that into dx exponential minus x squared, with x being omega over, or being that. Okay. Okay, and with dx being d omega over square root of 2 times omega naught. So there is also a square root of 2 and the omega naught in front. And look at the bounds. The bounds are plus infinite. And here this is 0 minus sorry, a bit wrong here. But VF is a cube alpha t minus t naught. So if I'm looking at an asymptotic description near the divergence point, near the glass, then this is going to 0. Okay, so basically this bound is going to minus infinity. Essentially, I'm describing things really near the universal point. And so the net result is that apart from a constant with a square root of 2 pi omega naught, I have essentially this result, this exponential term, which is the main dominant one. Okay, so now I can complete the formula above. I have the end term, which is the teacher, if you want, who is doing the job. And then you have the I to the power n minus 1. So there is n square root of 2 omega naught, which are constants, to the power n minus 1. And then there is this important factor, n minus 1 times omega naught squared over 2 vf squared. Okay, so we found the relaxation time in the de Gennes scaling sliding mechanism. Okay, so can you comment on that? And this is the next question. Look at that. This is the relaxation of the teacher of the class. So this guy has to move in the subway. But this is like a standard molecule in a standard glass. So this molecule has to do a free volume game. So it's already a very slow process. It has to move and push neighbors and the free volume picture we described so far. However, we say that the time scale for relaxation, which is the inverse of the probability here, is this one that we just described, but it's amplified, it's much longer due to the fact that now even though it's easy for them, you have to wait for every little kid behind to move in this little tube. So in any case, this is much smaller than P end. You can compute the normalization and see that this doesn't play a huge role, okay? But you see, the mechanism by de Gennes doesn't work at all in the bulk, because in the bulk, you first need a standard glass relaxation from the first monomer, and then behind you have an additional price. Even though this price is small, you have to pay it. And there is a huge number of objects, so N here is very large. So it's unlikely that in the bulk, the sliding mechanism will be efficient. But everything will be different if we go to interfaces. So sliding inefficient, and we keep to the free volume picture in the bulk. Now, let's go to thin films. Now, if we have thin films with a certain thickness H, well, then the situation is very different. And I told you that at the beginning. You might have chains that do that, something like that. Or something like that. We call that bridges. And we call that loops. Okay? And what is very different is that now that the teacher, remember, it's a kind of random walk process. It's a Markovian process, the polymer statistics. So we don't really care about what's going on after here. So you can only focus on what happens between those 2 points. So now the teacher is here, and the gate of the subway has opened, and the teacher is going one step outside. There is nobody here. You can move really easily. It's like a liquid-like motion. So P end, I mean, it's a suppressed penalty. It goes to 1. There is no more free volume constraint for the leader. Then the sliding mechanism becomes very competitive because you only have the motion of the kids behind, and they are much easier than free volume motions because they follow the leader. So that's the main idea by de Gennes. So bridges and loops matter, okay? Sliding matters. Okay, so let us now finish on the estimate of the effective glass transition of this polymer glass. What is the typical relevant size of such objects? For the system to relax macroscopically, for the film of polymer or the confined glass to flow, to relax, you need those bridges to exist, or those loops that you can see here, to go near the middle of the film so that most of the sample is relaxing. So you need on average to have if I assume ideal statistics with G monomers in a bridge inside from that point to that point. So we have ideal statistics. So you need typically to have G, which is h over a squared. That is the relevant length scale in the system. You don't care about the total number of monomers. What you want to measure is typically what is the distance between two interfaces. Okay? All right, so now we don't have, in this formula here, we don't have n anymore. That doesn't play any role. What matters is g. Okay? All right. So the relaxation time on average in such sliding mechanism, first of all, there is no end effect, so we kill that term. There is an amplitude here which is not meaningful, so it's of order 1. We just don't consider it. Actually, it's not of order 1. There's a 2 power n if you do the calculation. But near the asymptotic point where the time scale diverges is completely negligible. It's a constant term compared to an infinite term, essentially. But homework, you can check the prefactors. So this is just a constant number, and so we just keep this law. So it's exponential minus g minus 1 if you want, 2vf squared. And there is a constant here in front. And to be able to neglect that constant, in fact, I should have been more precise, just take the log of that. And so you end up with a constant term minus something like g, and g or g minus 1 is the same when you have large numbers. So essentially, you can write things this way. And since the free volume is vanishing near the asymptotic moment, that is why we don't really care about the prefactors I was mentioning before. Okay, so the asymptotic behavior, and same for the g minus 1, is essentially given by minus. So sorry, the time scale should be positive. Why is there a minus? No, I was wrong. My mistake. It's a plus here everywhere. So we are just asymptotically dominated by this contribution. And g, we know what it is. So the time scale in unit of molecular time scale is g, which is h squared. My mistake again, sorry, there is a square here. H squared over a squared times all that. To vf squared. All right, so we found the time scale for relaxation with the de Gennes mechanism in confinement. And this is the log. Okay. So we said before that glass transition is equivalent to saying that this log goes to a certain value between 20 and 10, we said, occurs when log of tau over tau naught equals L, which is between 10 to 20, we said. So the glass transition is defined, effective glass transition for the sliding mechanism is obtained when L is equal to H squared over A squared, omega naught squared, 2, and then VF squared is what? Is, we know the expression, it's alpha squared, A squared, so A6, T minus T naught squared. We just replace by the free volume expression. It's a squared. And this is the temperature at which this equality holds is the effective temperature. So I can take the square root of all that. H omega naught 2 alpha A3 Tg minus T naught. And so it provides me the expression of the effective Tg with this new mechanism. So it's T naught. And then I have, let me see, I have H omega naught A square root of 2 alpha. And then A cube square root of L. So it's a linear dependency with H. And I will stop that because then you can I will stop there, sorry, because then you can finish the tutorial. There is no major point behind. But the important aspect is the following. We know that there is a bulk value for the glass transition. So this is TG. This is TG bulk. We know it, we discussed it in the first and second part. It's associated with the bulk mechanism. But now we are saying that there is a second mechanism where you have another way of relaxing, which is this TG tilde, that is tau naught plus something linear in H. Something like that. And so what Dejean says is that basically when you are at very large thicknesses, very large samples, well, you're dominated by the free volume picture, the bulk mechanism. The other one doesn't play a role. We already discussed that. But then at some point, there is a mechanism that is more probable, and it leads to a smaller glass transition temperature. That is this one. And so, sorry, up. And so this is explaining why on the experiment you see a glass transition that is suddenly sharply changes linearly with the thickness. And if you finish with the orders of magnitude in the tutorial, you will see that this typically occurs around 100 nanometers. So it's exactly what is observed in the experiment. There is a kind of mesoscopic length scale, which is much larger than the monomeric one, below which you start to see TG depressions. And so this model is good for that. So there are very good aspects. You see a linear behavior in H that is reminiscent of the reality. We see H star, a typical value here, which is in the good order of magnitude. You see also that if H is bigger than this H star, then TG is always equal to TG bulk, no matter the size of the polymer chains and so on and so forth. So this is also a very robust experimental fact. But there are drawbacks. What is bad in this model is that N does not matter. The size of the polymer chain doesn't matter, which is not observed experimentally. Experimentally, if you have one molecular weight or one size of polymers, you have one depression. If you change the molecular weight, you have another line with a different slope. So the slope is depending on the molecular weight, on capital N. And in this very simplified picture, this is not the case. Secondly, it seems that TG is always bigger or equal to T naught. When the sample size goes to 0, the minimum value is T naught. And again, this is wrong experimentally. There are observations below T naught. So the model doesn't capture those fine details. Okay. So just to summarize, it's now in the confined glasses community, which is a restriction of the glass transition community. There is this first mechanism that allows to explain some features of the reality, but not others, and it's still an open problem. So people are working on that and trying to understand it. All right, I will stop that. It was a pretty dense tutorial, I guess. So I will let you digest that and come to me with questions if you have some, or if you want to discuss, feel free to contact me. Okay, any question? No?
Yes, I have one.
Yes, please.
Is it possible to make like if we have a bulk with big pockets of free volume, it could be described with a model like this one?
Okay, so I don't know if I understand correctly your question, but this idea of free volume has been also used to describe composite material. You can, for instance, fabricate a glass, and in this glass, you have some inclusions that are, for instance, you know, like a sponge, a vacuum or a pocket of air or atmosphere. Think about a sponge, but assume that the sponge is glassy. Well, it's a system where you have a lot of interfaces. So it's not as simple as a film where you have really one typical thickness between two interfaces. Here it's more a sponge, so you have plenty of interfaces. But then you could really calculate, you look at exactly the same problem. You look at the probability of relaxation when suddenly you have bridges between two free volume regions. And this might be explained with this type of mechanism. So I don't know if this is what you had in mind or.
Yes.
Okay, so this is a very good suggestion. You can also think about mixtures. People are studying, especially in the industry, think about the tires of your cars. Michelin, for instance, companies, they are trying to optimize the material so that it doesn't become glassy too quickly. You know, you want it to stay soft, to adhere to the road, but there are some glassy modes depending on the speed. And so you can optimize the glass transition property of your tire by putting some composites, either by adding some inclusions, but that are not vacuum, that are solid nanoparticles here, or by putting mixtures of different polymers. And so then you can also rethink about all this problem by having some binary mixtures of different free volume problems, okay? And then again, there is some interesting problems to invent and to solve. Any other question? There is one chat.
There's one in the chat, and then I have one.
Okay, please go ahead. I will go to the side after.
The fact that there's a distribution of n, and not only one big N for all the polymers.
That is another degree of complexity.
Okay.
Already, we are not able to find the good description with purely homogeneous or monodisperse samples. But of course, now, if there is really a dependency with the molecular weight, meaning that if I take another molecular weight, perhaps I will see something like that. If I take a third molecular weight, I will see something like that. So depending on N, you might have different behaviors, even for pure samples. So now what you're saying is that if you have inhomogeneous sample in terms of polydispersity, you might be dominated by the largest molecular weight, by this part of the distribution. So you might see some composite TG of H curve that is convoluted with the distribution of molecular weight, and so it won't be straight anymore. It might be a bit rounded, and it will be dominated by the large molecular weight. So you have to do the calculation. Question in the chat. How could we observe stuff under T0? Haven't we said that it's 0? I'm saying that now we are not talking about bulk materials. We are talking about confined materials for which the transition is at smaller temperature. So we are shifting all the picture. But I'm not shifting the value of T0. T0 is the bulk value. So if you take a very small sample, then it will be very unstable at some point, and it will become a liquid and not a glass anymore, which means that T0, I mean, the glass transition temperature is pushed to very small temperatures, even below T0, the bulk value. Does it answer the question? No, there is a comment by Delphine who said that not in VFT. That is true. In VFT, T0 is non-zero, but that's another part. You're not sure you get it. Okay, so Baptiste, you think about it, and then you contact me, and we discuss by email, okay? Or by Zoom. Any other question? No, so then I wish you a very good weekend, and feel free to contact me if you have any question. Thanks. Bye-bye.
Thank you. Goodbye.
Thank you. Bye. Thank you. Bye.